who's in someplace in China. So yeah, let's get to it. So I got the Pi working. This is what you guys should see when you first boot it up. If you put my image on it, and you have to put the image that well, you don't have to put the exact one that I uploaded, but uh, the one that comes on the SD cards in the kits is the 32-bit operating system, and since we're going to be doing 64-bit assembly, uh, you can't do that in a 32-bit OS. The instructions just don't work. So so this image is the 64-bit beta version that they released in May, and future versions of the OS will be full 64-bit, but um, well, most of them. So the Raspberry Pi 3 and 4 have 64-bit capable processors in them. The 1 and 2 do not, and also the Raspberry Pi Zero, which have any of you ever heard of, even know what that is? So it's like really small and low power compared to these things. So it the current models have only a 32-bit capable processor in them. So they'll have to maintain a 32-bit OS for sort of legacy products and the zeros. But the 64-bit version is what we need. Now, from the user perspective, there's basically no difference. It looks and feels basically the same way. Right now, not all of the software that they include with it is 64-bit capable. So, for example, the Raspberry Pi operating system, they have a license with Wolfram, so there's a version of Mathematica on it. We don't have, or there's not a 64-bit version of it for this processor architecture yet. Hopefully they'll get that up and running, because that was actually one of the really nice selling features of the Pi, is that you basically had Mathematica for free, and because Mathematica is a pretty expensive piece of software. So anyway, okay, so I pre-installed a decent amount of stuff on here for you guys to use. The Wi-Fi, let me make sure I'm clear on that. So the Wi-Fi thing is up there, and that's where you pick your network. Uh, IoT is the one that you want, but in order to get it on there, you have to register the device. And the way you get your MAC address is just open up a console, type ifconfig, and then what you're looking for is that right there. So DCA632160739 is the hardware address of this Pi. Yours will be different. And so it's that set of numbers that you'll need for the registration page. And you'll have to do the registration on a different machine, like your laptop or something. Um, but basically, you'll just sign in. You'll put the hardware address of it, and then give it a description. So for the description, just if you have already done it, don't worry about it. But just use the sticker name, right? CSC dash Pi 4 dash whatever your number is. Or if you own it, then you can name it whatever you want. Um, yeah, so that's how you'll get these things on the network. If you've got Ethernet available wherever you're living, then you can just do that too and bypass the Wi-Fi entirely. Doesn't really matter. Uh, the I mean, wireless is, or sorry, wired is always better than wireless if it's available, but you know, depends on how your living unit is set up. Okay, so that's how you'll get the MAC address, and Jack, you won't have to worry about that, because you'll just, you're not on the school Wi-Fi. So if you're on, Wi-Fi of your own at home or something like that, then obviously that doesn't matter. It's only for the Wabash network that you need that. I also installed this handy dandy little calculator. Um, and this is a programming calculator. So, I mean, you can do all the usual calculations with it, but It also displays stuff in binary and hex for numerical data, well, or integer numerical data, which is kind of cool, right? So, you know, so if I wanted to see what that is in binary, uh, then it's that 32-bit number, and the bit positions are indicated there, right? So this is the ones place, twos place, fours place, and so on. And in this case, the number I put in is small enough to fit within a 32-bit number, and so all the rest of the 32 bits are just zeros because we didn't really need them. Um, so yeah, so it's going to display everything as 64-bit integers, um, and which for the positive ones it doesn't really matter, right? It's just um, uh, for the positive integers, you'll just have a bunch of zeros at the front if it's a small number. For negative integers, though, it's going to be the number of bits is going to be important, because how do we represent negative integers in what do we do? I'm seeing a lot of this from the peanut gallery back there. You remember two's complement? Yeah, those of you who took 101. Those of you who did not take 101, have you ever heard of two's complement before? Yeah. Have you heard of it before? Okay. So the way that we store negatives is, uh, so if I take this, well, let me just take a smaller number for the sake of demonstration. Um, like let's say the number A, which is 10 in base 10. Um, then, okay, there's the binary representation of it. Okay, it's a bunch of zeros. Uh, you might think that a logical way to store negative integers or positive integers is just to use one of the bits as a sign bit and say it's either plus or minus whatever, but that is not the system. So if I put a minus in front of this, um, then, oops, um, well, okay, here, let me just do this. Why did that not work? Okay. There we go. Okay. So that's the negative of it. So I'm using the twos or the ones, but let me actually go back to so A is that, right? A bunch of zeros and then 1010 at the end. If I take every bit that's a zero and flip it to a one, and every bit that's a one and flip it to a zero, then that's called the ones complement of the number. So if I do, for example, here ones of A, then notice that the bit pattern I've got is all of the zeros that I had before have been flipped to ones, and all of the ones that I had before, there were two of them, have been flipped to zeros. So it's just reversed all the numbers. Okay. If I then add one to that, then what would happen? Most of these ones are going to stay put, but down here on the small end, I'd have 0, 1, 1, 0. Yes? Yeah? Okay. So that's the twos complement. And so if I have that, in this case, it would be all those F's and then a 6 at the end. That is the binary representation of negative 10. Okay. And so, yeah. Now, the thing is, if I were to then do this plus A, okay, that is not what I wanted. I think I probably have to put a bunch of zeros in front. But anyway, the if I take let me do twos of A. If I take that number in binary and I add it to the number that I started with, which was a bunch of zeros and then 1010 at the end, then what's going to happen? What should happen? I should get all zeros, right? Which means that the two numbers are, one was the negative of the other because you added them up and you got zero. Um, okay, so the that's the system for storing negative integers, two's complement. And the intro chapter in the first book, the ARM 64-bit assembly, goes through that. It doesn't talk in there about floating point. We'll deal with floating point maybe a little later. Um, the floating point format stuff is a little bit more exciting. So anyway, but we'll get there. Uh, okay, so but what I meant about the 64-bit stuff is if I were to be doing this in, say, 32 bits, then when I flip all the bits, not everything, like only some of it's going to flip, right? Because if I only have 32 bits, then it would be this part right here, and then I wouldn't have all those ones from the top row in front. We'll basically, for the most part, always work with either 64-bit or 32-bit integers. Um, and when you guys define something in Java, an integer, usually it's defaulting to a 32-bit or maybe 64-bit integer. Um, unless you explicitly tell it that you only want like a Boolean, for example, that's going to be a single bit. But in memory, it probably is going to take up more like at least a byte because you've got, you got to put it somewhere. Um, so yeah, and then floats uh, are depending on which version of like Java or C or whatever you're using, are either going to be 32-bit by default or maybe nowadays 64-bit by default. But usually, if you define a float, it's 32-bit, and if you want a 64-bit, then you do a double for double precision. That's just what we call it. And you there are a very limited set of circumstances under which you need to go any further than a double precision floating point number. So anyway, okay, so that's two's complement, and this little thing can be kind of handy to do some of that arithmetic or double check yourself. Uh, okay, so let's get into some of the assembly. So what I thought we could do to sort of start off here is let's actually write a program in C. Okay, a real short program. It'll look basically just like Java from y'all's perspective, with a few minor exceptions. And then what I'm going to do is I'm going to compile it, but we're going to look at the assembly that comes out. Okay, so let me start a new program here. And let me save this somewhere. Okay, so I'll make a new folder. Where's the new folder button? There it is. Okay, so we want oops. Okay, so the editor I'm using here is called Genie, and it's the little like thing with the genie coming out of it. Um, and it's an IDE. There's a billion of them, right? But one thing that's kind of nice about it is that the build stuff, so the build commands, it's pretty intelligent about what build commands to use, and if you give it the correct file extension, it's going to recognize that and do syntax highlighting and stuff like that. So So let's write a really simple, and let me blow up the font here so you guys can see it a little bit better. That's not what I want. View, change font, and then let's, okay, that's probably a little easier to read. Okay, so I'm just going to define a simple function called main that's not going to do anything exotic, um, except let's just like add two numbers together. So if I did something like um, int a equals 5, int b equals 6 or 7, say, and then I could do int c equals a plus b. Okay, so something really, really silly. You'll notice that this looks pretty much just like Java syntax, except there's not like public and private and some of those kind of things that you have to throw in. Um, but whatever. And the int main void, right? So what am I doing there? I'm okay. And so the function takes no input, right? That's the void part. What about the output? It's an integer, okay? And the convention here is then what I could do is I can uh, return 0, okay? Or, well, really, I could return anything I wanted. I could return C, the number C. So the return value here, at least on Linux, it's pretty typical that if the program is successfully completing to return 0, and that's the exit status. And so then what you can do is if you have sort of like um, an error function that would happen or would trigger if there was some problem, then you could have the program exit with a status other than 0, and that can help you in debugging. Um, but for our purposes, right, we'll just return 0, and that's the end of it. Okay, so let's compile this thing. And so to do that, I mean, I can just hit the run button, and that'll just do everything for me. Or I can pop open the terminal, and let me blow up the font on this too so that it's a little easier to see. So let's see, we want to do preferences, monospace regular. Let's do 20 point. Okay, so that hopefully is a little easier to see. Is that okay? Yeah, okay. Okay, so then I need to go to the directory that I was in, and so I'm going to do cd programming, and if I hit tab and start typing, it will autocomplete if there's a unique match, so you can get real fast in going through your things. And then I called this C example, and then I've got example1.c. Okay, so what I need to do is um, I'm going to assemble this rather than compile it. Okay, so if I compile it, um, then okay, what did I mess up? Derp. Mm, what did I mess up, guys? Mm, oh, that's it. Yeah, it's a blank file. There we go. Thanks. Okay, good. So the syntax here is GCC. Uh, GCC stands for GNU C compiler. Um, example1.c is my input file, and then -o is my output. I want to output this to the program called just example1. And then on Linux, the way you run this So if I type ls, that lists the files in the current directory. You see how there's a example1.c, that was the program, and then the example1 is the actual executable, and it's highlighted in green because it's an executable. And then the way that I run that is you type dot slash and then the name of the executable. Okay, that's just a Linux thing, and that will execute it. And of course, from our perspective, absolutely nothing happens because um, adding some numbers. It wasn't printing anything to the console or anything like that. So it executed that arithmetic, but we don't really see it. Okay, so but what I'm going to do instead is, so normally, guys, what you guys did with Java or C, or well, how many of you guys have actually done any C or C++ programming? Okay, so when you guys write stuff in Java or C, right, you just compile it, execute it, and it runs, right? So, and depending on the IDE you're using, it might have a single button that does all of this crap for you and just launches the executable, and that's the end of it from your perspective, okay? But what we're going to look at is actually the layer in between. So this is half the point of this course, right, is to look at the layer between your high-level code and the actual executable file, okay? So stuff in the middle is called assembly. So what I'm going to do is I'm going to assemble this, and the syntax is very similar. Well, actually, let me do this. So a convention that I picked up is if you handwrite assembly, you give it the extension .asm. If you have the machine produce it for you, you give it the extension .s. Doesn't actually matter, right? The extensions don't mean anything to the compiler and stuff. It doesn't care what the extension names are. But the nice thing about that is then you can tell easily by looking at the file extension which files you wrote manually and which files were generated by a program. Okay, so same syntax, right? It's just instead of GCC, I'm going to use AS for assembler, okay? And then let's see what we get. Okay. Oh, no, I'm sorry. We need to use GCC, but I don't remember the syntax for it. Okay, so when in doubt, pop over to the internet. Okay, so the AS program would be what we would use if we had already produced the assembly, okay? To take an assembly file and output machine code. We'd have to still use, oops, GCC. We'll talk about that later. But okay, so let's do GCC assembly and remind myself what the syntax is for this. Once it loads, nice and slow, duck, duck, go. All right, so here's something on Stack Overflow. So basically what we have to do is there's an option that we pass to the GCC program to have it spit out just the assembly, and I don't remember the syntax for it. Um, um, dash S. Okay, that's what I thought. Okay, so then I wanted, it was example1.c, and then I'm going to output this to example1.s. Okay, so now there's a file that's been created, example1.s, and if I open that up, then this is what we get. Okay, so this is actually what the machine was executing in our completed executable file. Each one of these lines, or almost, corresponds one-to-one to a chunk of the binary in the executable. Okay, now let's just kind of look at what we have here, and sort of talk about what all this stuff starts to mean. Okay, so the stuff at the top is basically just like what's the file name that we're dealing with, what's the what architecture are we on, and ARM v8-A is the particular processor architecture that the Pis are running on. So 64-bit ARM, and then so let's get to the meat of it, which is the stuff down here. Okay, so what's going on here? We've got this thing called SP, which stands for stack pointer. We'll talk about that in spades later. And then we're moving data from, so this W0, W1, what are these things? Okay, so those of you who took 101, what's really inside the processor? Where does data get manipulated inside the processor? In the registers. Okay, so inside a processor, there are, depending on the architecture, some number of these things. The 64-bit ARM capable stuff, they have 32 general purpose registers. Okay, and they can hold, each one of them can hold 64 bits worth of stuff. Okay, if you go back to older machines, so like your original Intel stuff from back in the day, they started out, the 8086, it had 4 registers, each of which was 8 bits wide. Okay, so not a whole lot. But if you want to actually add 2 numbers together, those numbers have to be in registers to actually be manipulated. So you would have to load them in to a register either from memory, or in this case, I had hard-coded numbers. So I would have to load those things in and then give an instruction to the processor to add them or subtract them or do whatever it is I want with them. Okay. Now, so those of you who took 101 with me, right, we did this with the made up Brookshire architecture. In that architecture, we had 16 registers, each of which held 8 bits worth of data. It was sort of an 8-bit toy machine. And then we had, for that particular architecture, 12 instructions. That was it, right? And you guys saw that we were able to do quite a bit of stuff with those 12 instructions, although we had to do a lot of work in the process. The architecture that we're using here has a lot more instructions, which is for better and for worse at times, but some of them are going to really make our lives easy. So for example, you guys can probably guess what the sub instruction does, I would hope. Substitute or subtract, okay? The Brookshire architecture did not have a subtraction instruction, okay? So how did we do subtraction on those machines, or the Brookshire architecture? We had to manually compute the 2's complement and then use addition. Well, it's really nice. We've got the built-in instruction here for subtraction. You don't have to mess with it. Not shockingly, you've also got addition, okay? And then what else is going on here? So what instructions do we see? STR, we also see LDR, we see move, and we've got addition, subtraction, and then down here at the bottom, there's also this return instruction. Okay, so what are all these things doing? Well, how do I load data into a register? On the Brookshire architecture, how did I do it? In one of the memory cells. Okay, so in the Brookshire architecture, there were actually two ways to do it. I could take data from memory and stick it into a register, or I could take a specific number and store it into a register. Okay, and this architecture, same kind of thing. So the difference between here, the move and the load, is where the data is coming from. Okay, so if I want to store a specific number that I've pre-selected, then I use a move, right? So move W05 is going to take the number 5 and stick it in register W0. Okay, good. And then the load instruction, LDR, is going to load a register. That's where the R comes in. And then the syntax here is, what register am I sticking the data into? Okay, W0 or W1 in this case. Where is that data coming from? Well, it has to come from somewhere in memory, right? Okay, so the thing that's to the right of which register is a memory address. Now, does that look like a memory address to you? SP, 8? Doesn't look like one, okay? On the Brookshire architecture, when we did this, you had to explicitly say what the memory address was, okay? 2A or F5 or whatever, right? Here on this architecture, it's actually relatively nice because it allows us to do relative addressing, okay? So there's a, when we run this program, a segment of memory is dedicated to be called the stack, okay? And those of you guys who have done data structures, right, what is a stack? Did you guys talk about these stacks and heaps and? Right. So I can put, it's a segment of memory that I can push things onto and I can take things off of. Okay. Now, we actually have a little bit more flexibility here that we can read things. We don't have to pop it off of the stack to read it. We can load it out of the stack, but it's not really a stack in that sense, right? That you have to push and pop. Um, So, okay, but what this is doing is, so the SP12 or the SP8 or whatever is allowing me to do basically the stack pointer points to a specific address in memory, and then I'm going to load things that are above it or below it by an offset number of bytes, and that's what the 8 and the 12 are indicating, is basically how far away from this base point am I. Okay, we'll talk a lot about the stack later, so we don't have to really uh, do tons and tons with that right this instant. But point being, it's loading from a specific cell in memory, but we don't have to actually know what that address is. So this is one of the things about programming on more modern architectures, right? So we have here, we're running everything on a machine that has an operating system running that's sort of in control of the machine, right? So the operating system is going to tell us what segment of memory we get. And what segment of memory is off limits because it's using it for something else, right? So the OS is sort of the traffic cop that keeps all this stuff working. Well, what about if there's no operating system? Then what? you've got full control. You are the operating system because there's literally only one thing running, whatever you give the machine. Okay, so if we were working on an OS-less machine, and this is uh, nobody really programs like this anymore, for the most part, then you could specify whatever memory addresses you want. Okay, and it would be up to you to keep track of where you were putting things so that you didn't screw yourself up, right? Or like have one part of the program messing up another part of the program. I think the situations where you would be doing this sort of low level bare programming would be any of you guys played with Arduinos, right? So there's no OS on an Arduino. You load in instructions, it just executes them, right? And it's got memory in it, not much, but it's got some, right? And it's just you can do whatever you want to it. Um, Another example of this where you don't have an OS would be if we look back at some of the older game consoles, so the 8-bit Nintendo, for example. How many of you guys had one of these when you were kids? 8-bit Nintendo, awesome. Does anybody still have theirs? Or did your parents get rid of it in some garage sale? Yeah. See, my dad got rid of my 8-bit Nintendo, and I've been cursing. I told him one day I'm going to be really mad at you for that, and that day came a few years ago because now I want it to program. So it only took 30 years, but whatever. Um, so yeah, so on the original 8-bit Nintendo, for example, you basically had full control as to what memory addresses you used. There were a few exceptions, so certain segments of memory were kind of reserved for the processor. Uh, and on the 8-bit Nintendo, certain memory segments were tied to things like the graphics chip or the audio chip or some of so there was some specialized stuff. But basically, um, with the original Nintendo, you had the cartridges. The cartridge ROM could be, I think, 32 kilobytes, and that's how much memory address space you had. So the Nintendo or the processor that was in it could address 64 kilobytes worth of memory. Not a whole lot, right? Um, and the cartridges would start at the halfway point is where they would be mapped to the memory. Um, anyway, so but there's no operating system, right? The operating system, if you will, is you pop the cartridge in, you turn the machine on, and it starts executing whatever's on that cartridge. That's it. No OS, no nothing. Now, your Xboxes and stuff nowadays, they've got operating systems and stuff, and it's all fancy schmancy. But back in the day, you had to keep track of everything. Okay, so we'll talk more about the stack pointer and stuff later. Um, but let's kind of look at what's going on here. So, what am I doing these first two instructions? Well, the first one is I'm loading the number 5 into a register. And then the second one is I'm storing that out to memory to keep track of it for later. Okay, great. And then what am I doing for the next two instructions? Same thing, loading 7 into the register, sticking it out in memory someplace. Okay, great. And then how do I add things together? Well, first off, I need to put them into registers, right? Now, the if I want to add two numbers, those two numbers have to be in different registers to start with, right? Can't put two things in the same bucket. All right, so I'll take uh, the number that we stored two numbers out to memory, 5 and 7, okay? And 5 was offset from the stack pointer by 12 bytes, and 7 by 8 bytes, okay, whatever. We'll talk about those numbers later. But then I need to load them back in, and so I've got what's now in registers 0 and 1. What's in register 0? The number 7. What's in register 1? 5, okay? And then I want to add those two things together. Yeah? Okay? And so the addition instruction is the next one. And what's that going to do? Well, what do you think the syntax is here? Right. In this case, right, you could, either way that you might think to read it is correct, but the destination is listed first. So where are you sticking the answer? Okay. What two things are you adding together? What's in W1 and W0? Okay. So the so what before that instruction's executed, what's sitting in W0? 7. After that instruction is executed, what's sitting in register 0? 12. Okay, the sum, right? So the number 7 has been destroyed in the sense that it's no longer sitting in a register. So if we had wanted to keep track of that number, we would have had to have stored it into memory someplace or copied it to a different register before we did that instruction. Now, in this case, we did the former. We put it out into memory someplace so that we could refer to that number later if we needed to. Okay. In this program, we don't, but we theoretically could have. Okay. And then what's the next instruction doing? Well, that's taking the data that we just computed and storing it out into memory, right? We might want to be using this sum for something later on, so we better stick into memory just so we've got it. And then the last instruction, the move W00, is well, let's look back at the source, right? What was my code originally? Okay, what was my C code? That is this part right here. Okay, so return 0 is going to be this instruction. I put 0 into the 0th register, and then I return. Okay, so your high level code, C, Java, whatever, right? One line of high level code may be multiple lines of assembly. But each line of assembly corresponds precisely to one machine operation, okay, one instruction for the processor, and it's going to do those instructions in line, okay. Okay, so does that kind of make sense? Hopefully, Jack. Hopefully, you're doing okay too. Okay, so let me pause. Questions, preguntas, fragens. Is it too early? Yeah, you guys need to learn how to drink coffee or Red Bull or whatever. You know, I hear Red Bull gives you wings.
So why don't we start with the subtraction and then at the end do the addition with the SPs?
The stack pointer, right? Okay, so the basically the stack pointer is a memory address, and so we need to grow the stack, and then when we're done, we shrink it. So the at the beginning, we subtract 16 from the stack pointer to grow the stack. Okay, and now you might say, why do you subtract? Well, the stack grows downwards, not upwards. Okay, so if I've got a memory address, then there are memory addresses that are lower in number, and there are memory addresses that are higher in number. And the stack grows downwards. Okay, so that's why I'm subtracting from the stack pointer. And so what that does is it says, okay, when the program started, the stack pointer was this. Okay, so this is sort of the starting stack pointer. And then I'm going to subtract 16 from it in this case to give myself 16 bytes worth of memory that I'm going to then do stuff with. All right, right before I terminate the program, I no longer need all that memory, right? So I'm going to return the stack pointer to its previous value and then return control over to the operating system, and it could allocate that memory for something else. Okay, so yeah, so that's the very first and last thing that will happen is you need to grow the stack to be whatever you need and then shrink it at the end. Now, you can do this multiple times, right? So you can have part of the program that grows the stack and then shrinks it back, and then another part that does that also. So it's not like you have to know. Uh, it's not like you have to only do this at the very, very beginning and the very, very end. That will be important for like later when we start talking about recursion, how you actually program something that's recursive on, in assembly. The stacks will be growing and shrinking while the program is running, not just at the beginning and at the end. Okay. Good question. Yes. Well, okay, so it only ever goes back 12. Let's see how much stuff do we have stored there? Um, so, right, because how much data are we actually using here? Each of these integers, how much data are they using? Well, what did I define them as in my C file? I mean, they're ints, but how much data is that? Okay, I know the answer, but I'm so being all Socrates today, huh?
Is it 8-bit?
8-bit? No, it's bigger than that. 32-bit. Okay, and 32 bits is how many bytes? 4 bytes. Okay, and that's why these offsets here are 4, 8, and 12. Okay, those are multiples of 4 bytes. Okay, so why did we have to offset the stack by 16 if we only actually use 12 bytes? Because you have to. So I ran into this the hard way last year. Um, on the Raspberry Pi, the stack pointer must be a multiple of 16. Okay, so if it starts as a multiple of 16, how do I keep it a multiple of 16? I have to subtract 16. So I actually allocated here 16 bytes worth of memory, even though we only actually used 12 of them. Is that seem like we've wasted 4 bytes? Yes, but you have to. Okay, so if I changed this 16 here and then correspondingly that one there to a 12, thinking, oh, well, I'll just use exactly the amount of memory I want, it won't run. It'll crash. Okay, now if you run this in an emulator, it'll run. Okay, so this is what happened to me last fall. I wrote a program on my laptop in my Linux virtual machine and ran it in an ARM emulator. Ran perfect. Great. Give the code to the students and say, okay, add some stuff that does whatever to it. And they do that and it doesn't work. And then they notice that on the Pis, the original code I gave them also won't work. And I'm like, what are you talking about? It doesn't work. It works fine. I ran it on my laptop, no issue. Well, that was the problem. I was running it in an emulator, and the emulator doesn't care what the stack pointer is, but the hardware actually does. So on the Pi, the stack pointer's got to be a multiple of 16. And so if we needed to use, for example, let's say we were storing 5 32-bit numbers, then we would have needed to grow the stack pointer by 32 bytes instead of 16, right? So it's always got to be a multiple of 16. Uh, the stack pointer itself. Now, memory addressing relative to the stack pointer can be whatever it needs to be. Okay, but the stack pointer itself has got to be a multiple of 16. That's just defined by the architecture. Um, yeah. And actually, one day I'll show you guys exactly that problem. We'll write something in on my laptop in the and run it in the emulator, and it'll work fine. And then we'll do the same thing on the Pi and Kaputski. Okay, to illustrate that. So that's one reason, by the way, why I know it's kind of was a pain in the butt to get the Pi set up. You know, you had to flash the image to the SD card, and that took half an hour, and then write all of that stuff. That's why I wanted us to use these things for the semester rather than just doing all of this on a Linux like server and emulating it, because we wouldn't run into some of these issues, and we wouldn't learn from actual hardware. Okay, is that Gucci? Yeah. Okay. Um, all right. So good question there. What else? And some of these questions are going to take weeks to answer, but um, why is it that we're putting like? Doesn't W0 seem like it's special in a way? Okay. Yeah, it sort of is. And so there's a convention, because like, where do we put the number 0 to return it? The exit status code. Where did we put it? W0, not W1 or any of the other ones, right? Uh, and so there's a convention about when you've got functions passing data back and forth, where the functions should expect the data to be coming from, and where they should put their answers when they're finished. Okay, so there's a convention for that, and uh, we'll talk obviously a lot more about that. Um, let's see, what else? Why are these things called W0? So let's actually change my C file example. Okay, so what is if an int is 32-bit, how would I get a 64-bit integer if I wanted one? A long, right? Okay, so a long or a long int, like so. Okay, so same code. Let's reassemble it. And then now let's look at it. Okay, so now how much is the stack pointer being offset by? 32, because instead of storing 3 or 4, I guess, 32-bit numbers, I'm now storing 64-bit numbers, okay, because I did long int instead of just int. The code looks almost identical with a couple of exceptions. How many bytes does it take to store a 64-bit number? It takes 8, not 4. Okay, so then notice the offsets from the stack pointer are all multiples of 8 now rather than multiples of 4, because that's how big the data is. And then also, where are all the W's? They're not there. Okay, well, except for that one at the end, right? So what is register X0 versus register W0? Say it again, I'm sorry. Not in this case, no. So W0 is the 32-bit smaller end of X0. Okay, so X0 is a 64-bit register. W0 is the lower half of that. Okay, and depending on the type of data you're using, then so W0 and X0 are physically the same thing. Just W0 is half of X0, the lower half. Okay, and right. But then, so here at the end, why do I have W0 whereas I was having X0 in all the other cases? Yeah, the 0 at the end, I didn't redefine that as to be a long. I just said int still. Okay, so the compiler or the GCC program, when it spits out the assembly, it's going to do, right? Oh, it's 32-bit. I'll use W's. 64-bit, I'm going to use X's. There are also other things that we'll talk about, like um, these registers all store integer data. There are separate ones for floating point data, and conventions for moving things back and forth and converting the data and stuff like that. Um, there's also some special registers for what are called SIMD. So SIMD stands for single instruction, multiple data. So this would be stuff like if you want to do linear algebra really, really fast, or like compute dot products of stuff, there are specialized instructions that can do that much more quickly than doing it one by one, right? And we'll talk about that way later, like basically like when fall break would be if we had a fall break, but we don't because Corona. So, speaking of Corona, have you guys been keeping track of the news lately? Yes. So, what happened yesterday that everybody found out about in the world of higher education? Yeah, UNC, Chapel Hill, University of North Carolina at Chapel Hill. What happened to them? And so they sent everybody home. Well, yeah, yeah, exactly, right. So they pulled the plug on their semester. Um, yeah. Now, granted, it's a big school, right? But it's not like they had 15,000 quarantine beds laying around, right? How many do we have? Well, yeah. Yeah. So what do we have on campus? We've got like, I think, 18 isolation rooms in Tripit, and I think roughly 15 to 20 beds in the quarantine house, right? So that's not a whole lot, right? And if we're at like 2%, like if we were at 5%, we'd be really, squeezing. Okay, so this is why the whole mask thing and sanitizing and hand washing and not going to parties and not throwing parties on the weekends. Frat guys gonna glare at you. Um, yeah, don't do that because if we see a spike of cases like they're seeing, then what's going to happen? Everybody's going to get sent home. And you guys remember how much that sucked last semester? Yeah, it would suck even more, right? So let's not do that. Also, please don't kill Professors Blix or Warner, right? Because if they managed to get this virus, that would probably kill both of them. I mean, they're both relatively elderly, right? Huh? Oh, Kubiak? Well, yes, it would probably kill him too, but huh, I don't know. There might be some professors you would want to die, and no. But yeah, like Makubia, Kubiak, Blix, Warner, right? If any of them got this, they would probably be goners because they're, in their 60s or whatever, 60s or 70s. So let's not kill them. Um, all right, so good. Um, all right, so back to what's all going on here. So um, the goal for us is to start writing programs in this assembly language, okay, but writing straight to this. Okay, so for the sake of demonstration, what did I do today? I wrote something in C, had the machine spit out the assembly, and yay, I've got the assembly, right? What's the real point of this class? We're going to write the assembly directly. Okay, so no more high level stuff. And in particular, if I were to have written this program by hand, it probably wouldn't look exactly like this. So for example, if all I wanted the program to do was to add 5 and 7 and that's it, right? I probably wouldn't have been storing that stuff out into memory because I don't care. I'm just going to add the two numbers and that's the end of it, right? Um, Also, some of this other stuff like the offsets and some of this other, gobbledygook, uh, I probably wouldn't have handwritten that unless I absolutely knew that it was necessary. Okay. So when the machine is going to spit this stuff out, right, it's not necessarily the case that every single one of these lines is needed um, to actually have this thing run. Um, but the compiler, GCC, is going to spit out stuff. Um, and yeah, so what we'll sort of start talking about then is how do you what are the different instructions that you've got? What lines are necessary to have here? What ones aren't? How do we store, for example, text? Okay, so how do you store text in a machine? There's a couple ways, but what's the simplest format for textual data? Hmm? Okay, an array of characters, but each character, how is an individual character stored? Well, a string would be a string of characters, but let's just forget the string, just literally one letter. How do we encode that? Okay, yeah, in Java, it's a car, but literally, like, what is that data actually? It's it's a byte of something or several bytes, depending on. But what format are we storing that in? In Java, what is it? In Java, it's stored in Unicode. In C, it's stored in Ascii. Okay, so how does Ascii work? Originally, Ascii was a 7-bit encoding scheme, and then it was later extended to be an 8-bit encoding scheme. 8 bits, okay? So how many things can you represent with 8 bits? Well, it'd be 2 to the 8th, right? What is 2 to the 8th? Hmm? What now?
Oh, is that 256?
Yeah, 256. Okay, so with 8 bits, or you can encode 256 different patterns. Okay, so we got 256 patterns, and how many letters do we have in the English alphabet? 26. We double that because we've got upper and lower case. We've got the digits. We've got punctuation symbols. Um, and if all we cared about was English, then we don't need 256 things, right? So let me actually pull up an ASCII table here. Um, so, and I've got a handout for this that I'll put up on Canvas as just sort of a reference. Okay, this is probably a little hard to read, but yeah, so like I said, original ASCII was 7 bits, and with 7 bits, you can encode 128 things. Okay, so the first 128 start with all zeros, okay, and that's a null character, which basically is how you tell in C that you've reached the end of a string. Is you put a little bit of a you put all zeros at the tail end of it, and then the program can say, oh, I just hit all zeros. That must be the end of a string. Um, a bunch of this other stuff is like communications things, like I'm about to start sending things. I just finished sending things. I'm acknowledging that you got it, and I'm asking if you got the data right. So stuff to basically encode message sent, message received, those sorts of things. So these are not printing characters. Um, we get to the printing characters. A space is actually an ASCII character because you got to represent that, right? Um, and then you've got the punctuation symbols, the digits, um, less than, greater than, equal to, semicolon, stuff like that. And then we start here with hexadecimal number 41 with the capital A runs down to capital Z, got some more punctuation, okay, great. And then the lowercase is at the there, starting with hexadecimal 61. What's really cool about this scheme, what do you notice about the lower and upper cases? Huh? Well, it's really 32 apart, right? So how far apart are they? In hex, what's the difference between 4-1 and 6-1? 2-0, right? Well, what is 2-0? That's hexadecimal. What does that represent in base 10? 32, right? Because you got a 2 in the 16's place and a 0 in the 1's place. Right, Evan? Yeah, we remember hex? Okay. All right. So that actually was really smart to do that because it means that it's real easy to convert something from lower to uppercase or vice versa because it's just a 32-bit, or not 32-bit, but an offset of 32 in base 10 or 2-0 in hex. Okay. So all you have to do is flip a single bit to make something from lower to upper or vice versa. Okay. Now, in Java or C, those of you who've done that, did you ever use the function to upper or to lower? Yeah, that's all it's doing, right? Is it takes something uppercase and converts it to lowercase or vice versa, right? And it's a pretty easy function to write because that's all it's doing is flipping a single bit if this data is stored in Ascii. Okay, great. Now, a little later, Ascii got extended, okay, to add, um, if we add one more bit, we get double the amount of data. So now we're up to an 8-bit, and this is sort of standard Ascii nowadays. And this got us like basically stuff that you would need in a lot of the European languages. So basically Latin letters, but that have decorations on them, right? So, for example, this one, the C with the little dangly thing, on it. That's called the cedilla. You need that in French because that tells you the difference between a hard C and a soft C uh, most of the time, right? So, if you say ça va, it's C with the dangly thing on it, not cava, which would be, I don't know, cava, type of champagne, I think. Yeah, yeah. Yeah. So, okay. So we've got basically a lot of the characters from different Romance languages and European languages that have decorations on them. Some extra currency symbols. I know it's a little hard to see here, but you've got the pound symbol for Great Britain currency, the yen symbol for Japanese currency. You've got like 1/2 as a fraction, 1/4 as a fraction, French style quotation marks. Some of these things are things that you could build like really cheesy user interface, like menu systems and stuff out of. And then towards the end, we've got some of the Greek letters, not all of them, but some of them. So alpha, beta, capital gamma, lowercase pi, capital sigma, lowercase sigma, mu, tau, capital phi, a circle with a dot in the middle, omega, the infinity symbol, phi, e, um, a plus or minus symbol, greater than or equal to, less than or equal to, the top and bottom of an integral sign. Um, and then a couple other things, the square root symbol, stuff like that. So basically stuff for mathematical representation. Um, Now, 256 things is a lot of things, but it's also not a lot of things because, poor Jack, uh, right? Jack's Chinese. How many characters are there in Chinese? A lot, like thousands, right? It's a ridiculous number because the language is just structured fundamentally different than Western languages. So, um, if you wanted to store like text in Chinese, you can't do it with ASCII. It's just there's not enough stuff, not enough room. Okay, and so what do we use instead? We use Unicode, where each character gets assigned, say, a 32-bit thing. And how many things can we encode with 32 bits? Well, what's 2 to the 32? A big number, right? Hopefully DuckDuckGo does math, right? 4 billion something, right? That's a lot of symbols. Okay, now Chinese has a lot of symbols, but it's definitely not 4 billion, right? It's only, a few thousand or something. So 32-bit Unicode, basically, we will never run, well, I shouldn't say never, because if there's anything to learn on a computer is that somebody will hit the limit for you. Actually, this number is sort of interesting because this is the number that broke YouTube. So uh, this is the maximum, well, one less than that, because if you count zero, 32-bit integer was how, unsigned integer was how YouTube was storing play counts. And then the Gangnam Style video came out, and people watched it that many times. And so the play counter broke because it overflowed and wrapped around back to negatives. So then they had to go back in and change the YouTube play count system to use 64-bit integers because 64 bits, how many things could we encode with 64 bits? A lot, right? That many, right? So basically, everybody on the planet would have to individually watch the Gangnam Style video billions of times each before we'd ever break YouTube again. I mean, we could do it, maybe. Yeah. So I don't know. Uh, I think the sun will expand and swallow up the Earth before that's going to happen. Um, yeah. Well, but that's like we're talking 3 billion years from now, right? So uh, let's just say that the end of the Earth is going to involve a lot of global warming, and then eventually being enveloped by the sun. So when the sun starts to run out of hydrogen and helium, it'll puff up into a red giant and swallow up Mercury and Venus and probably also Earth. But even if it doesn't swallow us up, we're going to be incinerated. So yeah, better get off the planet in a few thousand years. Okay, so right, so Unicode would be the answer for storing a lot more. Um, uh, well, to be able to extend the number of symbols that you can represent. So Unicode has all of the symbols from all of the different Asian languages, thousands of those. Um, it's also got stuff like hieroglyphics, right? It'd be kind of nice to be able to textually encode and record in a digital way, other than just pictures, hieroglyphics or other sort of ancient symbols. All of the emoji are Unicode symbols, but they won't. They denied the petition to add Klingon to it, so I'm still kind of bitter about that. You can have a poop emoji, but you can't have Klingon. I think that's a little ridiculous. So, okay, so C by default is going to operate with ASCII stuff, and for just typing simple things like "please type your name" or "the answer is," right? For that, ASCII is more than sufficient. Um, and so some of the programs that we'll write that will involve textual data will have to encode that in ASCII or know that it's being encoded in ASCII. So, for example, if I wanted to, if I had a program and I said, please type your name, right? Then you type something. Well, how is the computer going to know that you're finished typing? Or that if I've got the string that's got your name in it, that it's how long it is? Well, if it's 1 byte per letter, and then what's going to be at the end of it, the null terminator that tells you you're at the end of the string. Okay, so you have to know how that's going to be encoded to be able to process it and do something with it. Yeah. Okay, so that's probably good for today because it is 9:15. So I'll go ahead and quit the stream here, and everybody's got their Pi fired up, and it looks like you got dear old Wabash. Yeah. Okay. Good. So yeah. So the first assignment was to basically get the Pi working so that you can actually start doing stuff with it, and make sure it's on the network so you can get to Canvas and whatnot. And so then we'll start doing, excuse me, actual programming. Please have a look at the beginning instruction. I mean, the introduction chapter, because that kind of goes through a quick review of hex and Ascii and stuff like that. If just to make sure you guys are clear on all of that, and let me know if you got questions. All right, so I'll kill the stream and see you guys later.